In today's lecture, we are going to discuss about T flip-flop as a series of lecture on digital electronics and flip-flops. We have discussed about SR flip-flop, D flip-flop and JK flip-flop. So today we are going to discuss about T flip-flop. T flip-flop is also known as toggle flip-flop. T flip-flop is obtained from JK flip-flop. The output of the T flip-flop toggles in each clock pulse, and that is why it is known as T flip-flop. So this is the circuit of a symbol of a JK flip-flop. So J and K are the two inputs. This is the clock being given. It has two outputs Q and Q dash. If you see when J is equal to K is equal to T, then it becomes T flip-flop. That is, if J is equal to 0, K is equal to 0. If J is equal to 1, K is equal to 1. Only these two states exist. Right? So instead of two different inputs, I can give one input. Here I can give one input. Inside lies the JK flip-flop. The function of JK flip-flop is hidden inside this. So if T is equal to 1 is given, it acts the same way as that of JK flip-flop, where J and K will be equal to 1. So this is the basic principle of T flip-flop. It again has the same applications as that of JK flip-flop. This is the circuit diagram of T flip-flop. The inputs will affect the output only when the clock signal changes from low to high for positive or from high to low for negative. However, when an edge is applied to the clock input, the flip-flop will hold or latch the last output if T is equal to 0 and will toggle it to its complement if T is equal to 1. This is the T flip-flop. If you see here, the circuit diagram is same as that of JK flip-flop, right? Can you see this is J and this is K. So we have interconnected a joint J and K, and a single input will be given here which forms a T. So here we'll be having only two conditions when T is equal to 0 and T is equal to 1. When T is equal to 0, J and K will be equal to 0. When T is equal to 1, J and K will be equal to 1. And this is the truth table. This is the truth table. So here you can see when T is equal to 0, here there is no change. And when this is equal to 1, here it toggles. And this is the characteristic table. So as you all know, characteristic table is the input versus the present state and to find the next state. So when the present state is 0 and the input is 0, the output will be 0. Similarly, when the present state is 0 and input is 1, the output is 1. When present state is 1 and T is equal to input is 0, the output is 1. When present state and input are same, then output is 0. So this is the excitation table. So it's given in reverse, right? When present state and next state is given, what will be the output is given by excitation table. Then now we have the characteristic equation for the T flip-flop. So characteristic equation is one which denotes the output. How the output is represented in a Boolean expression form. That is what characteristic equation is. So here we have only 4 levels, and so we'll be using 4 cell, that is only 2 bits are there, and 4 levels, and so we'll be using a 4 cell K-map in order to find the next state. So the next state Qn plus 1 is given by T Qn dash and T dash Qn. So if you see here, this is an XOR gate, that is one is complemented and another one is not complemented. So if you see here, this is an XOR gate. So T XOR Qn will be the output. Boolean expression for the next state. So this can be used to draw the logical diagrams. Now coming to the assessment part, how many input terminals does T flip-flop has? Write the characteristic equation of T flip-flop. So it's XOR of T and a present state. Thank you.